Preston, what'd you guys get for the mean?
We had 47.
And how did you get it?
By doing the mean.
I'm asking Preston. Okay. Guys,
You guys did Preston.
I'm asking Preston. Preston, how did you find the mean?
We had all the numbers in there.
Okay. And how many? There were 11? Yeah. Okay. So we divided by 11. So about 47.6, right? Okay. Median. Let's do this table. 58. How did you get that?
It's the middle number.
It's the middle number. Okay. When will there be one middle number and when will there be two middle numbers?
When there's an even number.
When even number, how many will there be?
If there's an even number, there's 2.
Right.
If there's an odd number, it's 1.
Yeah. So what do you do if there's two middle numbers?
If it's 2 middle numbers, you subtract, and then you add and then divide by 2.
There you go. So you basically take the average of those, right? Okay. So what about the mode, Charlie? Okay. How did you know that? The number that occurs the most. Okay. Good. All right. What about the range, Erica? What about the range?
It's the highest number minus.
Okay, so subtract the highest minus the lowest. So what'd you guys get?
61.
61. All right, good. All right, guys, listen. So the first 3 things that you calculated there, the mean, median, mode, and mean, median, and mode, are called measures of central tendency. Okay, what does that mean? What's a measure of central tendency? What is that?
Measure of what?
A measure of central tendency. That's what
Like
mean.
like an average. It's like an average of how much something occurs.
Maybe. Mean is considered the average, right?
Central tendency is like the middle.
Kind
The
of.
amount.
Yeah.
The amount of the middle.
Yes. What does tendency do? What does tendency mean? If I
You
tend to
usually
do
do it.
something, I usually do it, right? If I tend to do something, I usually do it. What's central mean? The middle, the center, right? So a measure of central tendency means that this data set that we have right here, this data is centered around one of those numbers. It tends to be around one of those 3 numbers. This is what we had. We had 47.6 and then 58 and 63. Now, so why do you think we need 3 of these measures? How come we can't just have 1?
Because it's a mean, medium, and mode.
And why do I need 3 measures of central tendency?
Medium, and mode.
Let me ask you a question. Does this data, is it centered around one of those more than the other?
Yes. They're all centered around 58.
58 more than the other 2, right? How come this one's not a good measure of central tendency this time for this data? It's really high, isn't it? Okay, how come this one's not a good measure of central tendency this time?
It's not.
Well, no, the whole number's okay. It doesn't have to be a whole number. But look at where it is in the data.
In the middle.
This one. Where's this one?
Nowhere.
It's down here, isn't it? If we were to put it there, it's pretty low, isn't it? How come this mean is low this time? Why is it too low?
There's 2 outliers.
Look at these 2. Look how low
That would
they are.
actually, I think that the mean would be the best.
You think the mean is the best still?
Because it's in the middle.
This one?
Yeah.
47.6?
That's in the middle.
Look at where it is.
It's in the middle.
No, it's pretty low.
It's in the middle of everything. Like, if you take it off, let's say I had 100 numbers. It's in the middle. So I'm saying.
Oh, but of this data.
Of this data, it's in the middle.
Yeah, but there's not
I
100
feel like
numbers.
it's the best representation because it includes
Yeah.
every single piece of
You
it.
think mean this time is?
Because 58 is high in the data than low.
This one is high?
That's high in the
I
data.
think it's
If you count these two, you're right. It's
You
high.
have to count that though too because it's in the data.
Well, and that's the reason we're getting ready to talk about standard deviation. Okay, because Logan thinks that these two are outliers.
yeah.
If they're outliers, and until you do standard deviation, you don't know. But if they truly are outliers, then this mean is not really good. Because it's making your central tendency be too low. Okay?
But even if they're outliers, they're still part of the data. So how do
They
we cancel them out?
are, but if we were to describe this data, we would say that it's kind of centered around 58.
How? Go ahead and
Because,
explain how.
because of if these two are outliers, and we're about to find out if they are.
Right, but you're asking what is centered around that data? Right
If
there?
we were to describe this data,
Right.
we would say that this data tends to be close to 58.
Who says that? Is that your opinion on that?
That's mathematically correct.
All right.
Because that's what a measure of central tendency is. It's looking at that data and saying, where does this data tend to be? And if those two are outliers, then median's the best one. We don't know that yet, so you might be right. We got to figure that out. We got to figure out if these two are
How would
outliers.
you know if they're outliers? If they're like,
We're going to do something called standard deviation, and that'll tell us. Okay, so I'm getting ready to show you. All right, range. What'd you guys get for range? 61. So you got that by doing 63 minus 2, the highest minus the lowest, right? All right, so the next thing that we want to do is standard deviation. Okay? So range and standard deviation are not measures of central tendency, they're measures of variation. Okay, now there's lots of variation in this room on hair color,
no, not really.
but not on gender,
Like.
right? Okay, so what does variation mean? Oh, thanks.
I have a question.
What? There's differences. So measures of variation tell you how much difference there is in the data. Do you think if you're a company and your parts are coming off the manufacturing line, do you think you want lots of variation or little variation, right? So we need to figure out how much variation there is in this data. Like, what if these were measurements?
That'd be very, very bad.
That would be bad, especially the 2 and
That'd
the
be
5,
like
right?
Capable of killing.
Yeah. Exactly. So this has a lot of implications for a company, like making a car part, right? And if they have lots of variation in this one part, there's probably going to be a recall down the road, right?
Yeah.
Exactly. Which costs them millions of dollars. All right.
I have a question.
Yes.
It's way off topic though.
Okay.
Do we really have referrals?
What?
Do we really have referrals?
Have what?
Referrals?
I think so. Yeah. I haven't heard what the final decision was. Yeah. Okay. So guys, let's look at this formula right here for standard deviation. Okay? So I want you to understand what the formula means. They use a lot of Greek symbols here.
Yes.
Okay? This symbol that stands for standard deviation, but it's called theta. Okay? But it stands for standard deviation. It's equal to, this symbol right here is sigma. Anytime you see a sigma symbol, it means to take the sum or add it all together. So it's the sigma, and then you're going to take each x value and subtract, this is mu, but that's the mean, and square it and divide by how many ever data points you have. We have 11 data points. So I'll show you on the next page. We're going to do this. So we're going to do it in a chart form. So in this first column, all you want to do is write down your data points. So from the front page, you're going to write down your data points in the first column. Guys, the only person that should be talking right now is me. So from the front page, in the first column, write down your data points. All right, so now we're going to take each one of those data points and subtract the mean. So this one we're going to do 2 minus our mean, which was 47.6, and that's negative 45.6. The next one, we'll take our data point 5, subtract our mean, 47.6, and you get negative 42.6. And you're going to keep doing that all the way down. 48 minus 47.6, which is 0.4. Okay? So you're taking this data point, subtracting the mean. Then once you have those answers, you're going to take that answer and square it. So negative 45.6 and square it. Oh my goodness. That's the last time I'll listen to Casey, Nate.
Yep, never listen to Casey again. You don't know what he's talking about.
Yeah, it's 45.6.
Yeah. And it's 42.6 too. He had me second guessing myself. Okay, so go ahead and finish out this table, and we'll go around here in a second. All right, so I got the first 3 down there for you, but subtract your data point minus your mean, and then take that answer and square it. All right, finish filling that out. This is not 1.6, this is 0.16. Very good. Making all kinds of mistakes today. All right, Jalen, what'd you guys get for this column right here? 49. Okay, 1.4.
It's a negative.
No, it's positive.
Got it.
It's the x value minus the mean, so this becomes higher now. So it should be positive. Okay, Jeremiah, what about this one? 7.4. Brad, what about this one?
Which one is it? 58. 10.4.
10.4. Trevor, what about this one? 11.4. Logan, 12.4. Lucas, 14.4. Last two, 15.4. Okay, let's talk about what they are squared. So Zeke, do you have 1.4 squared? 1.4 squared, what'd you say?
1.96.
1.96, yeah. 7.4 squared. Do it real quick.
You gotta do some work.
So
How you do it?
7.4 squared.
Oh.
No. Yes. Okay, there's the square button right here. So 7.4. What'd you get? What'd you get? Jonathan, what'd you get?
54.76.
Yeah. Okay, Charlie, 10.4 squared. 108.16. Cameron, 11.4 squared. 11.4 squared, right here. It's not 5,000. It's not what they're saying. They're on something else. 11.4 squared. Oh yeah, try that one again. What'd you get? What'd you get, Cameron? 11.4 squared.
1.9.
Okay. Jack, 12.4 squared. Yep, 153.76. Erica, 14.4 squared. Yep. And Blake, last one, 15.4 squared. Yep. And guys, you need to write that down twice. You need that for both of the last two. Okay, now look. In our formula, we've done each data point minus the mean, and we've squared it, so we have all of our squares. But remember, this sigma means that we're supposed to take the sum of that. So we need the sum of that. So we're to Casey. 5,024.
It's probably wrong coming from
Point,
Casey.
what? Yeah, he got it right that time.
You sure it's not 0.4?
Now, so here's where we are in the formula. So we have this whole numerator now because we've taken the sum of all of our squares, right? So we've got the numerator 5024.6 or 56, isn't it? 56. Okay, we need to divide that by what? What's the N stand for? What'd you say, Joe?
11.
Why 11? Because there's 11 numbers. It's just like mean. We're going to divide it by how many ever there are. Okay, so when you divide that, you get a long number.
56.78.
Okay, hey guys, don't round. Everybody listen to this. Don't round until your final answer. So we're going to leave that whole thing in the calculator. I think it's 8-1 and the 8-1 repeats. Okay?
Yeah.
So we're going to leave that in our calculator and then take the square root. And then we'll round at the end. So now we just need to take the square root of that number. I did, hey, Morgan.
Well,
Morgan, it's enough. You're not here to correct people. I want people to ask questions. So, Erica, this top, the numerator, means the sum of all of our squares, and that's where we got the 5,024.56. We're supposed to divide that by n. N stands for how many numbers there are. So there were 11 numbers. So I did 5,024.56 divided by 11, and that's where I got this number. Okay, now we're just taking the square root of that number. Okay, so if we round that to one decimal place, it's 21.4. So our standard deviation is 21.4. Now, Jonathan's asking about how we know if this is what's an outlier now. Standard deviation kind of tells you what a normal distribution would be. Your mean is in the middle, so this is 47.6 right here. One standard deviation from the mean means that I would take my 47.6 and I would subtract my standard deviation to get the low end of this range. And then I would do 47.6 plus 21.4, and that would give me the high end of the range. So basically I'm doing this 47.6, and I'm going to plus and I'm going to minus the standard deviation to give me a range to see if I have any outliers. Okay? So when you do 47.6 minus 21.4, I get 26.2. So here's 26.2 right here. And then if I do 47.6 plus 21.4, I get 69. So this is 69 right here. So one standard deviation from the mean, our data should fall between 26.2 and 69. There's actually a percentage. It should be 68% of your data should fall within that range. Okay? Then you can go out and be even more confident and do two standard deviations from the mean. Well, if one standard deviation is 21.4, how much is two standard deviations? What do you think?
42.8.
You just double it, right? Two standard deviations. So instead of adding and subtracting one standard deviation, I would just double this and do two of them, 42.8. Okay? So when you subtract that, you're going to get 4.8. And so this two standard deviations, that's 4.8. And on the high end, if I add it, it is 90.4. Somebody just check me on that. I think it's 90.4.
Yeah.
95% of your data should be between those two standard deviations. Okay? So what's the only one that looks like it's not within two standard deviations of our mean? What data point is not between those two?
Let it be the 48.
Which one of these data points?
2.
2 is the only outlier. 5 barely made it, right? 5 barely made it in, but it did make it in. So 2 is an outlier for sure. Okay?
So, like, you have to do standard deviation every time to figure out
To
outlier.
figure out outliers, you gotta, like if you're in manufacturing, you've gotta figure out when it's coming off that line and you're measuring stuff, what's acceptable for you. Most of the time, they want 2 standard deviations from the mean. So they would accept, if these were measurements, they would accept anything from 4.8 to 90.4. Now, that's probably not measurements. They're probably gonna want, we'll do some measurements. The one you guys do tomorrow, the data will be a lot closer together. Okay, so really, if it was me, I wouldn't be accepted in this one. That one to me is way too close to the mean. I don't know. That just seems really weird. That one does to me. Okay, but they can run this test in a computer program, and that's what we're going to do tomorrow. We're going to put it in the computer so that you don't have to calculate this by hand, right? They'll just run it in the computer, and they'll know this is my acceptable range that I'm going to accept anything between these two measurements. But we've got to calculate standard deviation for
What are we
that.
going to use this like to make it like?
On our puzzle cube, so your guys are going to have to take your puzzle pieces and measure them and make sure they're within 2 standard deviations of each other, of whatever the mean is, right? Because what's going to happen if you've got a cube that's way off? Not going to fit together, right? So before you start gluing your puzzle pieces together, you're going to have to figure out, are my cubes within an acceptable measurement?
But didn't we already build a cube together with the pieces that we have?
No, just with the linking cubes. We're going to build them out of wood, and that's what you're going to measure.
Oh.
And we're going to glue them together and all that. Yeah.
Well, what estimate is like on the line? Like if it was 4.8, for example?
Yeah, it's still within the acceptable range according to that. Yeah. And it's really, as a manufacturer, how comfortable you are with it. Yeah. Okay, tomorrow we'll finish up and do a histogram, then I'll have you guys do one on your own, and then we'll work on putting this in Excel, okay? So no homework tonight. Don't forget to look at your grades, make sure those are all right. I'm kind of a statistics nerd because my background was in advertising research, and we tested television commercials. So this stuff, like I have a lot of experience in statistics, and so I kind of like this stuff. So the first thing that we need to add to standard deviation is this standard deviation formula that I gave you yesterday is for the population. And we're going to talk about what that means in a second. But that standard deviation formula is for a population. Okay, I'd put that on there. There is a different formula. It's not much different, but there is a different formula for a sample. So here's the formula for a sample. So that one's for the sample. Okay, so get that down. Take these out while I'm teaching.
My bad.
Okay. So population standard deviation and then sample standard deviation. Yes, Casey? Yep. Can you catch?
Oh, God. Two liars.
Butterfingers.
All right. So what's the only difference in those formulas?
There's
a 1 and a 1. Yeah, this one's in minus 1 and this one's in. what is a population? When you're talking about statistics, what's a population and what's a sample? What's the difference between those two?
Populations of females.
Okay, what amount?
I think
The whole amount. It's the whole amount. So if we were surveying freshmen in Owensboro and Davis County, the population would be all of the freshmen in Owensboro and Davis County, which is about 1,000 freshmen.
Wasn't
Okay.
just people up?
Huh?
Just people.
Yeah, populations are sure.
It's just people, right?
Oh, well, population can be, like in manufacturing, if I want to measure every piece that comes off of the line, that would be my population. So it is not just people when we're talking about statistics. Okay? So the population is the entire amount, right? What's the problem with surveying all of the freshmen in Owensboro and Davis County? Takes a lot of time. It's a lot of people. When I was in advertising research, we were testing television commercials, and we were trying to predict what the entire population of the United States would do, whether they would buy that product based on that television commercial. Do you think we surveyed the entire population of the United States of America? Absolutely not. It's 300 million people. It's, number one, it would cost us too much money, right? Number two, it would be hard to do. So we took a sample of that population, and we could be confident to a certain degree, and we'll talk about confidence levels here in a second, we could be confident that that sample represented the population. So in manufacturing, do they measure every piece that comes off the line if they're trying to make sure their machines are accurate? No, they measure a sample, right? They measure a sample. Now, the more samples that you measure, the more accurate you're going to be. So you're kind of always in statistics playing a balancing game of, I want to measure enough so that I can predict what the population will do, but I don't want to measure as so much that it's going to cost me a bunch of money. Okay, so that's always the balancing game that you're playing in statistics. So this is the sample standard deviation. Now, you guys told me that this is the only difference in the formula. Because I'm not dividing by as much, right? I'm dividing by one less. That's basically what this formula is saying, right? What's going to happen to my standard deviation if I divide by one less? What's going to happen to my standard deviation if I divide by one less? Will it go up or down if I divide by less? So think about 12 divided by 3 versus 12 divided by 2. It goes up, doesn't it? Right? So if I divide by less, that means my standard deviation goes up, which means that I'm going to accept more. Remember we talked about yesterday the range that we would accept? I'm going to be accepting more. And that's because I can't be real sure because I'm doing a sample, but I'm pretty sure that that sample is going to predict the population. Okay? Now, here's the other thing I need you to write down is about the confidence levels. And we talked about this yesterday, but just so I don't have to give you another page of notes, these are all the notes for this unit. So one standard deviation from the mean, and I really should put plus and minus in front of that. Remember, we added one standard deviation and we subtracted one standard deviation. One standard deviation from the mean is 68% confident. Okay? So we can be confident 68% of the time if our numbers are one standard deviation from the mean. Two standard deviations from the mean is 95% confidence. So that's the typical standard. Most manufacturers and the company that I worked for, they didn't like 68% confidence, right? That was not confident enough for them, but they were happy with 95% confidence. You know, that other 5%, that's okay. So you guys would probably be happy with 95% on test, right? Not so much 68%, but 95%. So they were pretty happy with this. Plus or minus 3, by the way, I don't think you have to know this for your quiz, but plus or minus 3 standard deviations is 99.7% comments. So that's the reason they don't care to go to 3 standard deviations, because there's not a big jump right there, right? But there's a big jump from 1 to 2. Okay, so they want to do the 2 standard deviations because they want that confidence level. They want that jump. But there's not a big jump here, so they don't worry about 3 standard deviations. Okay? So that's all the notes that we need to add. So we just need to finish that histogram on the back, and then you guys, then you guys can do one of these on your own. Okay. All right. So let's look at the histogram.
So we did everything that we did yesterday was wrong.
No. What do you mean everything? No, I just added some stuff to it. Because we're going to be doing a sample one today. Okay. Well, actually, we'll do the sample. Look at that. How come it does that sometimes? It drives me nuts. I'll have to erase it now. Okay. So let's go back here to the histogram on the back. Everybody done with this? I know Jonathan's got to get it, but he can get it from somebody else. All right, so a histogram is pretty much a bar chart, but it has intervals for the bars instead of just like, usually bar charts you have categories, but your categories on a histogram are intervals. So on this one, our data goes from 2 to 63, right? Okay, so we want something lower than 2 and something a little bit higher than 63. So I'm going to count by 5. So it just seems easy to me. So I'm going to go 0 to 65 are going to be my intervals. So we need an XY axis here. And on this, on the y-axis, we're going to label that frequency. Everything's positive, so we only need the first quadrant here. And down here will be our intervals. And when we get ready to do this in Microsoft Excel, I'm not sure if we'll get that done today or tomorrow. The Microsoft Excel instead of calling it intervals, they call it bins. So that means the same thing. So I'm going to start at 0 and I'm going to skip 2 lines, and this will be 5, so my bars will be pretty wide. So 0 to 5 will be one interval, and then 5 to 10, 10 to 15. And I'll just keep counting by 5s, but I'm skipping a line between. All the way to 65. And then we only have 12 data points, so on our frequency, we can just go from 0 to 12 and just count by 1s, because we only have 12 data points. So just label the y-axis, just count by 1s. Anytime you're doing a graph, make sure you put your numbers on the line, not between the lines, or, 1 is this line. Okay. Now, you guys don't have to write this down. I'm going to write the data points down just so that we don't have to flip back and forth. So this was our data, 2, 5, 48, I'll write that down when you guys are finishing this up. You don't have to write this. It's on the other side of your paper.
No, it's on the graph at the very top.
Oh, it is there too, you're right. You could look there. I can't scroll up, so I'm just gonna look here. Do this. Okay. So we're gonna look at our data and see how many numbers are between 0 and 5. How many numbers are between 0 and 5? 2. These two. So we're going to make a bar that goes up to 2. Like that. Okay? Now we don't have any numbers between 5 and 45. So we're going to skip all of those. And now we have how many numbers between 45 and 50? How many? Between 45 and 50 would be our next one. So 2 again. So it goes to 2 here between 45 and 50. A histogram, your bars are going to touch. And that's because there's not any space on this number line here. So on a bar graph, usually your bars don't touch together like that. Okay, how about between 50 and 55? Just this one, right? And then between 55 and 60, 1, 2, 3. And then between 60 and 65, there's also 3. What statisticians call a normal distribution would look like this. I do want you to get that down because I think on some of your homework, especially when you get to your puzzle cubes, they'll ask you if your data was normally distributed. So we're going to look at this data and decide if it's normally distributed. Your mean, remember, is supposed to be in the middle. Well, that's not mean. So our mean is supposed to be in the middle. And then that's supposed to be our highest point, and then it's supposed to go down on either side from there, right? So what was our means? Anybody remember where you have it?
47.6.
So it's here, right? 47.6. So in there, it's supposed to be our highest point. What do you guys think? Is this data normally distributed?
No.
No. I mean, this data, even if I don't count those two out here, this data is really our highest points in here, right? And we kind of talked about yesterday that our median might have been a better measure of central tendency, right? What's our median? You may remember what our median was? 58, was that right?
Yeah.
58?
Yeah.
Look at that. That's, the highest point is actually there, isn't it? So this one was probably a better measure of central tendency because that gets a little bit more normally distributed. It's not quite there. But now, our range, remember range tells you how far it's spread out. Look at our graph. Look how far spread out it is, right? There's a lot of variation in this data because it's so spread out. We got all this little stuff down here, and then this stuff's clumped together over here. Okay. All right, so you guys have one of these to work on your own. And my recommendation to you is have me check your mean before you do any of the back. Because when you do the back, you want your mean to be right before you do the back of it.
Yeah, we go.